Okay, and welcome to the third example. This time we're going to put a 0 in both of these two spots, so it's going to be slightly different from the previous two, not much. What we're going to find is it doesn't change the eigenvalues much, but it does change how the eigenvectors work. First off, let's ask that question, what's a minus I lambda? Or lambda I, we usually write it. Well, that's equal to 5 minus lambda, 0, 0, 5 minus lambda. And its determinant then is just 5 minus lambda squared, 1 squared. And when we set that determinant, that characteristic polynomial to 0, we get the idea that lambda is equal to 5, and it's equal to 5 twice. It's got an algebraic multiplicity of 2. In the last case, we could only find one vector with that eigenvalue. However, in this case, we'll find that there are several, or at least 2. So the first thing we might do is we might say, well, let's write this in the form a minus lambda I quantity times x is equal to the 0 vector. What we'll see pretty quickly is something a little bit intriguing, right? So we get this, x1, x2 is equal to 0, 0. And if we're in the business of thinking about this as a system of equations, what we'll find is the first equation says 0 is equal to 0, the second equation says 0 is equal to 0. Those things are manifestly true, but you'll find it doesn't tell us much about the vector x. And in point of fact, it is the case that if you take any vector x times a, any two-dimensional vector, you get back 5 times that vector. As one could figure out, because if we have x1 and x2 here, right, what we'll get is we'll get 5x1 there and 5x2 there, and that is just equal to 5 x1, x2. So that's interesting. So we don't really have any constraints. In fact, any old vector is an eigenvector of this matrix with eigenvalue 5. But let's go ahead and just play the game. Let's say, well, we didn't know that in advance. Let's just guess a vector. Let's guess v1 is equal to 1, 0. How'd I pick that? I like 1s, I like 0s. I don't like any other numbers. So if I've got that vector as v1, which does manifestly satisfy the constraints of 0 equals 0 and 0 equals 0. We can check, we can show it's an eigenvalue, and then you could say, well, is there a second vector? And I say, well, how about a different vector, which is equal to 0, 1? v2 is not a scaled copy of v1 in this case. These are different. You can't find a constant to multiply v1 by to get to v2. It can't be done. That means there are two different vectors. Now, there's nothing magic about these two vectors. In point of fact, any two vectors that aren't scaled copies will work. So you could have v1 be 1, 0, and you could have v2 be 1, 1, 1 minus 1, 1 literally anything, 0 anything. It doesn't matter as long as it's not a scaled copy of v1. Right? There's no uniqueness to these eigenvectors because there's an eigenplane. And in a 2D space where we only have x1 and x2, that plane is the entire set of real numbers in both directions. So it's what we call R2.